Hi everyone, thanks for stopping by to check out our talk. My name is Nate Veldt. I'm a postdoc at Cornell University. I'll be talking today about some work on localized hypergraph clustering. This is joint work with Austin Benson and John Kleinberg, who are both professors at Cornell University. So I'm going to jump right into things with a not too controversial statement, and that is that there are lots of data sets out there that can be modeled well by a graph. So a graph is just a bunch of nodes that share pairwise relationships. And one task that people like solving in graphs is graph clustering, which is the task of trying to find well-connected communities or clusters of nodes in the graph based on their edge structure. So modeling things by a graph is often a really good idea, but there are also plenty of instances of data sets that are actually better modeled by a hypergraph due to the fact that they have higher order interactions between data objects. So let me give you a few examples of what I mean by that. You can think, for example, of some categorical data sets where, for one example, you can think of an online forum. You can treat tags that are associated with different posts as being nodes in some hypergraph. And then every post will include one or a larger number of tags, quite often more than just two tags. And so you can think of the set of tags associated with post as being a hyperedge and model this entire data set as a hypergraph. And so if there are lots of different tags that show up in the same post, it's helpful often to think of these as a multi-way relationship between the tags and not just a whole bunch of pairwise relationships. Another example is retail data. So quite often it is useful to think about the things that a user purchases or maybe a set of products that a user reviews as all being nodes in some hyperedge of products. And just to mention one more example, you can think of physical proximity, where sets of nodes could correspond to, for example, a bunch of students, and hyperedges could represent students in the same class. And so this is really a group interaction and not just a bunch of pairwise interactions and pairwise relationships. So it's nice to think about things in terms of hypergraphs and hyperedges quite often in certain data sets. But methods for hypergraph analysis are not so well established or not as well studied as their graph counterparts. So we're specifically going to be talking about local clustering in hypergraphs. And what I first want to do is go back and talk to you about what local clustering looks like in graphs, because it has been studied a lot more extensively in the graph setting, not surprisingly, than in the hypergraph setting. So this is the basic premise of local graph clustering. You have some graph, potentially extremely large, and you have some region of this graph that's defined by a reference set or a seed set that I'll call R throughout the talk. And this is just a set of nodes. And what you would like to do in a local clustering application is find a good cluster of nodes, we'll call it S, that is somehow near R. And so one way that you can measure how good a cluster of nodes is using the conductance objective. This is by no means the only way to measure cluster goodness, but it's a very common one. This is what's known as a ratio cut objective because it measures a ratio between a cut score and some measure of the size of the cluster. And so in this case, if you look at the small example right here, the cut is the number of edges leaving the cluster and going to the rest of the graph. And so I've got a cut of 3 for this small example. And the volume is the sum of the degrees of each node. So one approach for local clustering is to use flow-based methods. This is certainly not the only way to find local clusters in a graph. You may have heard of the personalized PageRank vector, and there are lots of local clustering techniques based on random walk methods and PageRank diffusions. That's not what we're going to look at today. So in flow-based methods for local clustering, what happens is you minimize a localized variant of the conductance objective. And so we're still in the graph setting here, but what this objective is it's a ratio cut objective between the cut, but in the denominator, instead of just being the volume, what you have is a volume term that rewards high overlap with your seed set or your reference set R, and another term that penalizes including nodes that are not inside your seed set. So you're looking for something with a smallish cut, but you're limited in how far you're willing to explore the graph in search of clusters because you don't want to add too much stuff that isn't included in your reference set. And so there are actually a lot of different methods that fit this paradigm. All of the papers that I've listed right there all minimize some version of this objective that I've illustrated right here. And by the way, I'll just be calling this local conductance. And if you're really interested in learning more about flow-based local clustering in graphs, there is actually a great and very recent survey out by Kimon Fontolakis et al., and so you should check that out. So what does a flow-based method do? It basically works as follows. You have your set of nodes R, and let's say one thing that you'd like to do is be able to check if the localized conductance score for a certain cluster S is better than some parameter alpha, for example. And you can answer this question, is a cluster have local conductance better than alpha, by constructing an auxiliary graph, call it G prime. And what you do for this is you introduce a source node S and a sink node T, and you introduce a lot of specially weighted edges in the graph. And then as it turns out, if you construct this carefully, then solving a minimum ST cut problem in your auxiliary graph will tell you something about the localized conductance objective in your original graph. So if you compute a minimum ST cut in the graph on the right, then if the minimum ST cut is less than some value, then that means you have found a set which has localized conductance that's small, or at least less than this parameter alpha. And you can run this over and over again to minimize the localized conductance objective eventually. So these flow-based methods for clustering satisfy a lot of really nice properties. One of the key properties of interest that a lot of these methods satisfy is that they're strongly local. And what that means is they have a runtime that depends on the size of the seed set, perhaps, but it doesn't actually depend on the size of the whole graph. So I'm illustrating right here what happens with a method called flowseed, which is one of these graph-based localized flow methods. And what's happening here is the method starts from a set of two reference nodes, R, and it explores a small region of the graph, and it solves a minimum ST cut problem, maximum ST flow problem equivalently. And then it grows the subgraph a little bit, and it continues to do this until it converges on a good cluster. And by doing so carefully, it has a runtime guarantee that does not depend on the size of the entire graph, because it doesn't actually have to explore and see everything in the graph. Another nice property that is satisfied by a lot of these methods is called, referred to as cut improvement guarantees, where the basic premise is if you assume the existence of a good target cluster T that has good conductance, then you can guarantee that your output set S, that comes from running some local flow-based clustering method, your output set is going to have good conductance that's almost as good as T, assuming there's sufficient overlap. Okay, so that is previous work on local graph clustering, and what we do is we basically take this framework and we extend it to the hypergraph setting. So in particular, we are introducing a localized hypergraph conductance, and we show similarly how we can minimize this by repeatedly solving hypergraph minimum ST cut problems. And we have nice locality properties, so we prove that our algorithm is strongly local, and we also get improvement guarantees in terms of both conductance and normalized cut. Normalized cut is another ratio style objective that's similar to but not identical to the conductance objective. And so just to highlight a couple specifics right here, so we'll talk about what this objective is, but I wanted to mention that solving a hypergraph minimum ST cut problem can be significantly more general than solving a graph ST cut problem, so I'll say a few things about that in a couple slides. And I also wanted to mention as well, there have been a lot of previous results about conductance improvement guarantees in graphs, but our normalized cut improvement guarantees are sort of the first of their kind. And as a matter of fact, our analysis actually, as a bonus, sheds some new light on what happens also in the graph case. So actually our results prove some new things even for the graph case. So we'll just briefly talk about that at the end of the talk. So we construct an auxiliary hypergraph in a very similar manner to the way I showed you previous local graph clustering methods work. You take your hypergraph, you introduce a source node S and a sink node T and some specially weighted edges. And then the minimum ST cut problem in this hypergraph is the following I'm not going to go through it piece by piece, but you can notice that the cut terms and the volume terms have a subscript h because this is a hypergraph version of cut and a hypergraph version of volume. For the volume, we're just summing up degrees of a cluster, where the degree of a node is just the number of hyperedges that that node is in. And this should actually say the number of hyperedges that node I is in, which is d sub I. And so what happens is, if we can repeatedly solve this stcut objective for different values of alpha, which is just a parameter that we can change, then we can eventually minimize this hypergraph localized objective. And so similar to the graph case, we have here a cut function on top. In this case, it's a hypergraph cut function. And then we also have this term that encourages overlap with our reference set R, and another term that discourages overlap with things that are not in your reference set. So we should hang on for a minute right here, because if I had actually heard someone tell me all these things about a year ago, I would have a couple questions at this point. And in particular, I'd be wondering about this point is what it exactly means to solve a hypergraph stcut problem. The graph stcut problem is quite common. If you've seen an undergrad algorithms course, you have probably spent a good amount of time looking at algorithms for the graph version of the problem. But what is this hypergraph cut function? How does it relate to the graph cut function, and how do we solve stcut problems? And so what we do in our paper is we actually apply a recent generalized framework for hypergraph stcut problems that we developed in previous work. And so the basic idea here is, in order to get a generalized notion of hypergraph cuts, we assume that each hyperedge is associated with something that is called a splitting function. You can think of this as a hyperedge weight function. And then if you sum up these hyperedge weight functions at each one of the hyperedges, this gives you the overall cut. And what's unique about the graph case, which doesn't happen, what's unique about the hypergraph case, which doesn't happen in the graph case, is that you can penalize different cuts differently. In a graph, there's really only one way to cut an edge. But if you have, say, for example, a 4-node hyperedge, well, you can cut this into a 2-2 split or a 1-3 split, and there's no reason why we shouldn't say, well, what if I penalize these two different cuts differently? So this is a significantly more general problem than the graph stcut problem. So even though we've defined it here, there's still an open question of how can we actually solve this. And what we proved in our previous work is that you can do this under certain conditions on the splitting functions that you use, by reducing the hypergraph stcut problem to a graph stcut problem. And so what happens is you need to replace each hyperedge with a set of extra nodes, auxiliary nodes, and directed edges. And this will model certain cut properties in the hypergraph. And so we specifically, for our local clustering applications, consider one type of gadget. We also proved that our framework works for more generalized types of reductions, but we focus mainly for our local clustering applications on something that we call the delta linear penalty. So we reduce a hyper edge to the following little gadget that's parameterized by the value delta, and essentially what this is doing is it penalizes linearly the number of nodes that are separated away from the rest of the hyperedge. So if you separate one node from the rest of the hyperedge, it's a small penalty. If you separate 10 of them, it's a larger penalty, but the penalty overall is capped by a parameter delta. And so now we can treat delta as a tunable parameter that may lead to different or better or worse clustering solutions in practice. So importantly, we don't just directly apply this reduction technique to the hypergraph all at once, because what we want is a strongly local algorithm. In other words, an algorithm doesn't actually explore the entire hypergraph. And so what happens is we have our auxiliary hypergraph here that has the source node and the sink node. And what we do is we explore a small region around the seed set, or this reference set, as we've called it, R. And we perform a reduction in a small neighborhood, and then we solve a hypergraph minimum stcut by just solving the corresponding directed graph stcut. And then we carefully decide how exactly we will continue to explore the rest of the hypergraph. And all of the details are in the paper, and I'm glossing over them now, but if you do this carefully enough, you can actually find the minimum value of this localized hypergraph conductance without actually exploring the entire hypergraph. And this just mirrors what happens in the graph case. We are just looking at small subsets of the hypergraph and carefully exploring. So I wanted to quickly mention what these normalized cut guarantees are. The normalized cut objective is given here at the top of the screen, cut divided by volume plus cut divided by the volume of the complement set. And so we have a theorem here that basically just says if some unknown target set R, if some unknown target set T overlaps with your input set R, then we have some guarantees that amount to saying that the output set from running your algorithm has normalized cut that is almost as good as this target set T. And so there are more details about what that means and how this relates exactly to previous guarantees for conductance. There is some relationship, but there are more details in the paper if you'd like to read some examples for what this type guarantee might do for you in practice. So I'm going to finish with a couple experiments. So we ran some experiments on a Stack Overflow hypergraph. And so what this Stack Overflow hypergraph is every node is a question, a post on the data set, and there are 15 million of these nodes. And the answers for each user defines a hyperedge. So to be a little bit more specific with that, if you take all of the posts that have been answered by the same user, that defines a hyperedge. So a hyperedge is a set of things answered by a user. And then the tags in this data set indicate a set of questions that are sort of related together. And so you can think of these as being clusters, and it's an interesting question to ask whether or not it's possible to detect what these clusters corresponding to tags are if you have, say, for example, a small percentage of the Julia tags. Can you find the rest of the Julia tags by running a localized clustering experiment? So for this experiment, we took around 2% of the target cluster in each case, like the target cluster for the Julia tag, and then we ran our method, which we call hyperlocal, and we also ran some neighborhood baselines that basically look at a neighborhood of the seed set and make a decision about which of those neighbors to include in the cluster. And then we also tried doing something that's called a clique expansion. So you reduce the hypergraph to a graph just by turning the hyperedges into pairwise relationships. And then we ran flowseed, which is just a graph-based method for local clustering. And we see that overall, we're getting average F1 scores higher for hyperlocal. We also ran some experiments on an Amazon hypergraph, and in this case, nodes correspond to Amazon retail products. And the set of products reviewed by the same user corresponds to a hyperedge. So there are 2.3 million products and 4.3 million users, so 4.3 million hyperedges. And we just looked at the smallest clusters. These are sets of nodes that are associated with the same product category, like beauty or fashion or appliances. And using a small seed set, we ran, again, our baseline algorithms and our method hyperlocal, and we were able to get output clusters that have good F1 scores when compared to these ground truth clusters. But what's really the most interesting thing about this is just the fact that hyperlocal is able to solve a clustering experiment within a few seconds or a few minutes on this extremely large hypergraph. And so that's especially nice, and it's due to the strongly local guarantees of our method. So I'm going to go ahead and wrap up there. You can take a look at our code online, and there's my contact information if you have any questions. I hope you'll check out our paper. Thanks.